Hi there! Welcome to this video where we'll explore the bubble sort algorithm in JavaScript. Here's what we'll cover today. We'll begin by discussing what the bubble sort algorithm is and how it works. I'll explain the process behind bubble sort with pseudocode and then break down the logic. Then we'll dive into the code, walking step by step through each line to understand the logic and the implementation. And finally, we'll look at the time complexity using big O notation and see how bubble sort performs. Let's first start by talking about how bubble sort works. So as the name implies, the goal of this algorithm is to have the largest elements bubble up to the top or the end of the array. In this algorithm, there are multiple passes that are made over the array until every element is in the correct spot. And on each pass, the largest unsorted element is going to move its way up to the correct place towards the end of the array. So to visualize the process, we want to start from the first element in the array. We then want to compare the current element with the next one. And if the current element is larger, we need to swap them and move that larger element up the array. We'll continue doing this until the entire list is sorted. Let's take a look at an unsorted array and go through how the bubble sort algorithm will work. The first thing we want to do is compare the element at index 0, which is 16, to the element at index 1, which is 23. We'll compare those two, and we're looking to see if 23 is larger than 16. It is, so there will be no swap made, but we'll move forward in the array. Next, we'll compare 23 and 33. 33 is larger than 23, so it will stay where it's at. No swap will occur, and we'll move forward to the next pair in the array. Now we're looking at 33 and 39. Again, those are in the correct order, so no swap, moving on to the last two items. Now when you compare 39 to 19, 39 is larger than 19, so we need to make a swap there. After we make that swap, 39 is in the last index, index 4, so it is now sorted, and we're going to return back to the front of the array. So as you saw, 16 and 23 are already in the correct places, so are 23 and 33, but when we get to 33 and 19, 33 is larger than 19, so we're going to make that swap and bubble 33 up to the end of the array. 33 is now in the correct spot, so we just have these last three elements that need to be sorted. 16 and 23 are correct relative to each other, but 23 is bigger than 19, so we're going to swap those two elements, and now 23 is properly sorted. Now we look 16 and 19. Those are also in the correct spots, so there's no swap, and now the entire array is fully sorted. Now that we understand the concept, let's write out the pseudocode. So the first thing we want to do is define the function. We will call it bubble sort, and we will pass in an array called items. Let's take a minute to walk through the pseudocode. So the first thing that we want to do is create a variable where we're going to store the length of the array. That way we can use it down below in our code in referencing the length. The next thing we want to do is start our outer loop, and that's going to indicate the number of passes that we need to sort the array. And an optimization we're going to add in here is we're going to create a variable called swapped. That's going to track whether or not a swap is required throughout the iterations below, so that if it's not, we can exit the code and be done with the algorithm. We have the inner loop that's going to come in, and this is going to do all of the work of comparing the adjacent pairs all the way up through the array. And within that loop, we want to compare one item to the one that's next to it. So once we do that comparison, if that current element in the left slot is greater than the next element in the right, then we want to swap those so that we can continue bubbling up the larger item. Next, if a swap is required, we can use array destructuring to do that. And we'll have to then change our variable swapped from false to true to indicate that a swap was necessary during this pass. And if no swaps were necessary, then we want to exit out of those loops and just return the assorted array. So let's dig into the code. The first thing we'll want to do is get the length of the array. So we're going to create a variable const length, and that will be equal to items.length. So that's taking the length of our array items and defining it in a variable. Next, we'll create an outer loop. So this loop is going to control how many passes we make through the array. And since the largest unsorted element moves to the end after each pass, we want our length to be n-1. That'll be the number of passes to fully sort the array. So we'll create a for loop. We're going to let the variable I equal 0. So that's the index it starts at. We're going to have I go up and be less than the length of the array, which we defined above, -1. And we'll have this variable move up in ascending order. I'm going to take this closing bracket and move it down here under our pseudocode. So the next thing we want to do is create a variable that will serve as a flag for us and track whether any swaps were made in that previous pass. So let's start by defining a variable. We'll do let, and we'll call this variable swapped. And we're going to start by setting this to false. So we're making the assumption that on the first pass, there wasn't a swap needed. Next, we're going to create our inner loop, and this is where the adjacent elements are going to be compared in the array. So let's start with for. We're going to call this variable j instead of I, and we will start it at 0. For this inner loop, the number of elements that we need to check is going to decrease on each pass. So we only need this inner loop to run through the length, number of elements, minus I plus 1. So we're going to do j is less than length minus I plus 1. This will allow us to decrease the number of elements we're inspecting as the passes continue. And again, we're going to go in ascending order. I'm going to take this outer bracket and put it down here to close our inner loop. Next, we want to check if the current element, item j, is greater than the next element, so j plus 1. And if so, we'll need to swap them. So let's start with our if statement here. So if items j is greater than items j plus 1, again, I'm going to take this outer bracket and move it. And now I want to do my array destructuring swap. So if a swap needs to be made, I'm going to start with an array with items j on the left and items j plus 1 on the right. And I'm going to swap the order of those. So now j plus 1 is on the left, and j is on the right. And if a swap is in fact made, then I need to indicate that and change our variable swapped from false to true. Next, we'll add an optimization to stop the algorithm early if there were no swaps made during the last pass. That would indicate that the array is already sorted, so we can exit the loop. So we'll go down here. So our logic here will be if there wasn't a swap, so we use the exclamation point to indicate that a swap didn't occur. Then we want to instruct the code to break out of the loops. And this will exit early and show that the array has already been sorted and save time of continuing to iterate through it. And the very last thing we'll do is return the sorted array. So we'll just say return items. And then our code is complete. Now let's take a closer look at the time complexity of bubble sort using big O notation. The time complexity will depend on how many comparisons and swaps the algorithm needs to make. So in our worst case scenario, in which we have an unsorted array, our time complexity will be O of n squared. That's based on our outer loop that is going to run n minus 1 times, with n being the number of elements in the array, and the inner loop, which will run n minus I times, with I being the current index of the outer loop. So this leads to a total of n times n minus 1 comparisons, which results in our O to the n squared complexity. In the best case scenario, we encounter an array that is already completely sorted. And in that case, the time complexity will be O of n. That's because we will only need to make one pass throughout the array, and we'll have to make no swaps. And based on the optimization we coded in, we know that our loops will exit once it determines that the array is already sorted, which will give us that O of n time complexity. So essentially, that means that bubble sort is going to be inefficient for large data sets, but with our optimization, it can perform well on nearly sorted arrays. Let's quickly take a look at how O of n and O of n squared compare when visualized on a graph. Big O notation is used to describe how the time complexity of an algorithm increases based on the input. So as we have our input size grow down here, input size meaning the size of the array, that time is going to grow as well. So O of n, or linear time complexity, the blue line you see, that means that the time it takes to complete the algorithm will grow in direct proportion to the size of the input. For example, if we double the size of the array, we'll also double the time it takes to run. This time complexity will appear as a straight line on the graph, and you can see that with the blue line. In the case of bubble sort, O of n is going to be the best case scenario, so that's where the array is already sorted, and it only needs to make one pass through the array, and that's going to result in n number of comparisons. However, more likely is going to be the O of n squared big O notation, and you see that red line that has a much steeper curve. That's going to represent the worst case scenario where we have an array that is not sorted, and it will create a quadratic time complexity, which means that if we double the input size, or the size of the array, that means that the time it takes to complete the algorithm will increase by 4 times. So it's a much steeper curve that grows as n gets larger. So to recap, bubble sort is just a simple comparison-based sorting algorithm that is repeatedly comparing adjacent items and swapping them if they're in the wrong order. Today, we implemented an optimized version in JavaScript, which has an early exit condition to improve the performance on already sorted arrays. The time complexity in the worst case is O of n squared, and in the very best case for a sorted array, it's going to be O of n. Thanks for watching. I hope this helped you understand how to implement and optimize bubble sort in JavaScript.